Welcome and hello. This is a video exercise in HEC HMS. And in this exercise, we are going to be dealing with the gridded temperature index snowmelt method. All right, what I have on the screen here is the introduction to snowmelt methods in general. So what we want to do is download the files from this page here. This is the first link in the description of the video. And then we're going to do a couple steps on this page, and then we're going to go to a different page that focuses on just the gridded temperature index method. So scroll down just a little bit if you want to follow along. Click on the zip file here to download, then click on the download button. All right, so that downloaded for me. I'll go ahead and just close that. Let's go ahead and see what the files are. So Upper Truckee River, start, Upper Truckee River, and then inside here are the files for the HMS project. So I'm going to go up one level here in the directory listing, find a location on my computer that I want to save those files, and then just drag them over. And in my Windows machine, that will also unzip the files in the same process. All right, once that's copied over, I can delete the zip file. Now let's open up HMS and let's open up that project. So let's go File, Open, click the Browse button. Project, here's Upper Truckee River, and then here is the Upper Truckee River.hms file. So go ahead and click that, then select, and then here is our project. So we already have a number of parts to this project that have been loaded up, such as a basin model we're seeing here. I'm going to go ahead and unselect a few of these map layers here. We'll leave the discretization on, all right, because this is a gridded temperature index snowmelt method video. Besides the basin model, which is just a subbasin and an outlet, we also have a control specification that ranges from basically all of water year 2017, except for the last month and a half there. And then we also have some time series data and grid data and some terrain data. Some of that data we will be using, and then some of it we won't. We go back to the web page where we downloaded the files and scroll down a little bit. We see a table here that compares the three different types of gridded snowmelt methods in HMS. So if I click on the subbasin, for instance, then in the components editor down here for subbasin, we have a number of methods that are already defined, which have already been added to the project for us, such as the structured discretization. We can check out what that looks like, 2000 meters SHG. Also the canopy method. It's the simple canopy method, and here are the parameters for that. So without going through all these different methods, we're just going to assume this project is what it is and then focus on that snowmelt method. The snowmelt methods we have are listed in this dropdown with three separate gridded type of snowmelt methods. So the one that we're going to select for this project will be the gridded temperature index snowmelt method. Back to this table, we see a comparison between the three different types of gridded snowmelt methods. The temperature index method is the simplest snowmelt method in HMS. This method uses air temperature as a proxy for the energy available for melting the snowpack. This method is simple and flexible, and it's what we're going to be using to calibrate in this exercise. It's the simplest method. As you can see, we only need to specify a precipitation grid and a temperature grid, but not radiation, wind speed, pressure, or humidity. Below that, we have some tasks, study area, really an introduction to the project. And then if we scroll down here, we have a list of data that's already been saved for the gridded data sets. So we're going to go ahead and add precipitation and air temperature, but not yet. This is just the introduction. Right here is where we add the meteorologic model and begin the steps of this exercise. Once we set up the meteorologic model, what we see is three different options for the three different types of gridded snowmelt method. We're going to be using this option one. But before that, we need to add our meteorologic model and follow these first 7 steps. All right, so back to HMS. The first step is to create a meteorologic model. So I'll go up to Components, Meteorologic Model Manager, New. I'm going to call this Water Year 2017, and then click Create. The first thing I like to do after creating a meteorologic model is to click on that model and then click on the Basins tab right here and change the no to a yes and click Save. All right, after that, we can go back to the main meteorology model tab here. And a few things we want to check for this exercise is the unit system, unit US customary. We're going to skip over radiation. For precipitation, we want to set this to gridded precipitation right here. For temperature, we want to use gridded temperature. And then all the other methods for this MET model, we can just leave at none because this is the gridded temperature index snowmelt method. And then for replace missing, we want to change that to set to default. I actually ran into an error by forgetting to do this, and it was a good learning lesson. So I'm going to leave it at abort compute for now, and then we'll come back and fix that later. All right, and back to our web page here. If I scroll down to the bottom of the page, as I mentioned, now we choose a snowmelt method. For this exercise, we're going with gridded temperature index, option 1. There's also an option 2 here in 3. If I expand the width of the browser, a side menu pops up. It actually is pretty helpful for navigating. So what we have is an introduction here. All 3 of the options are going to use the same introduction and MET model setup. And then after that, we can just navigate using these 3 links in the menu, the same way we can click these 3 links down here. So let's click on option 1. And here is option 1. The first task here is to create a paired data components. So what that means is we'll go up to the components menu and then click on paired data manager. For the data type, we're going to select ATI melt rate functions, which is right there, new, and then I'll give it a name. We'll just call it ATI melt rate. It's going to be the only ATI melt rate we have. While we're here, let's go ahead and create the other pair data set, which is going to be an ATI cold rate function, new. ATI cold rate is the name, and then click create. Okay, close the manager, and now over here in the Watershed Explorer, we should have paired data, and now we have our cold rate and melt rate functions here. That was steps 1 through 6. Now the next steps 7 through 12 is, or 7 through 15 is where we define the data for these melt rate and cold rate functions. Here's the melt rate function here. What I want to do is go manual entry and then confirm that the units are degree Fahrenheit day colon inches per degree Fahrenheit day. And that's correct. So these units here are going to show up for the units in the 2 different columns of the table tab for ATI and melt rate. The values the instructions tell us to put in is 0, 25, and 9999 for the first column for ATI. And then for the second column, we put in 0.02, 0.05, and 0.11. And that is the melt rate, inches per degree Fahrenheit day, and save. All right, let's do a similar task for the cold rate. So I'll click on cold rate. And then for the paired data tab, I want to just confirm the units, and that is correct. So I'll click on the table here. And the values we're told to put in here is 0, 25, and 9999 for the ATI. Now the cold rate is going to be 0.01, 0.02, and then 0.02 as well. And then let's click save. All right, we're on the task 2 now of the instructions. So if you scroll down, that is right here. Parameterize the gridded temperature index snowmelt method. Back to HMS, we're going to start this task by creating a copy of the basin model. So this is the basin model that we have in view. It's our only basin model in the project right now. But what we want to do is right click, create copy. And this is going to be called almost the same thing, water year 2017 underscore TI or temperature index and copy. Now let's go ahead and open up that basin model and then make edits. So I'm going to click on the basin model and then zoom in. That was steps 1 and 2. Steps 3 through 5 is to set the basin snowmelt method to gridded temperature index. So what that means is we'll click on the sub-basin, either up here in the Watershed Explorer or in the basin model map. And then for the sub-basin here, this main tab, we're going to go down to our snow method and change that to gridded temperature index. All right, after that, we can click on the snow tab up here in the components editor, and now we can define all the data here. At the top of the components editor, we see a number of initial values right here, and they're set to default value by default. And I believe that just means 0 because the simulation will begin at the beginning of the water year when it's assumed there will be no snowpack. We're also provided a number of values to put in here. So for PX temperature, that'll be 32 degrees Fahrenheit. Base temperature, 32 degrees Fahrenheit. 0.98 for the ATI coefficient. The wet melt method is going to be constant value, which we have here, and the wet melt rate is going to be 0.1, and that's in units there of inches per degree Fahrenheit day. The rain rate limit is going to be 0.1 as well, and then dry melt method is going to be ATI function. So that's already set to ATI function. And this is where we specify the ATI melt function that we created and defined right here. We'll just select ATI melt rate. The cold limit in inches per day will be 0.2. And then for ATI cold rate function, we're going to use the ATI cold rate function that we defined as well. The cold rate coefficient is going to be 0.35. These are just numbers provided in the tutorial. And then the water capacity will be 3%. The ground melt method will be fixed value, and we will set it at 0 inches per day. Go ahead and make those changes and then click Save. The next step tells us to create a simulation run and then run it. So we'll go up to the Compute menu and then Simulation Run Manager, New. We're going to call this Simulation Run Water Year 2017 underscore TI. Then click Next. The basin we want to use is the one that we just created and assigned our Snowmelt parameters to. And next. This is our one and only meteorologic model, so click Next. And this is the control specification, which ranges for that water year 2017, most of it. All right, let's go ahead and close that. Let's select the simulation we just created and then click Run. And then now we ran into an error, and down in the message box here, we have an error and it says precipitation grid has not been set. And it tells me that the air temperature grid has not been set. All right, the instructions were helpful once again. What we need to do is come up to the meteorologic model. If you haven't already done this, expand that model so we see the gridded precipitation and gridded temperature icons. Click on each of them. First, precipitation. What we need to do for this grid name is select MRMS corrected, and then save. And then for temperature, same thing, except RTMA is the temperature grid that's already been created. And we can confirm that by going down to the grid data. Here's the precipitation grid, and here is the temperature grid. With that being said, let's go ahead and run the model. Okay, so now we come across the error I expected to see. And this basically says that precipitation is missing or invalid for 62 of the 62 grids on October 11th at 4 p.m. And this is the first grid that happens to have missing data. I'm in DSS view now, and if I navigate to that MRMS corrected.dss file and then scroll down to October 11th, we see there are some missing records here. So between these two records of 2 o'clock to 3 o'clock, and then the next one is 5 o'clock to 6 o'clock. So we're missing a couple hours there. Anyway, that's just a quick little explanation as to why we want to set to default that missing values parameter right here. Replace missing and set to default. Okay, so let's go ahead and run the simulation, and it should run this time. All right, looks like it's working. The simulation is complete. What I want to do now is look at the results. So I'll click on the results tab right here, and then I'll expand the simulation run, click on the simulation run, and then I'm going to click on the subbasin right here, Upper Truckee River S10. I want to compare the results for observed snow water equivalent and snow water equivalent. So here's observed snow water equivalent, and here is snow water equivalent. I'm holding down the control key so I can select both records at the same time. We have a little preview plot down here, but I can also show that plot up in a separate window. I'm going to modify the plot properties real quick. Here we go. We can see it a lot better now. In red, we have the observed results for snow water equivalent during the simulation for water year 2017. And in blue, we have the computed snow water equivalent, which is far less. And that's why we need to start calibrating. The instructions also tell us to add in the air temperature and precipitation. So I'm going to go ahead and click precipitation and then click air temperature. I'm going to go ahead and plot those all together. I'm not going to change the colors this time, but we see the hyetograph, the precipitation depth in the top plot. And then in the lower plot, we see the same two curves for snow water equivalent, as well as the air temperature, which oscillates here with the axes kind of labeled on the right side. So clearly, as the precipitation falls at a low enough temperature, that threshold temperature, more and more snow will fall and then ultimately melt later in the water year. That was step 9. Step 10 tells us to look at the results for the outflow, which is the outflow and observed flow. So I'm going to go observed flow is right here, outflow is here. And if I click on the plot and expand it, we now have the black hydrograph is the time series data representing the observed flow, and then blue right here is the computed flow. If I zoom in briefly on some of these numbers, The blue hydrograph is a larger number right here, so we're seeing that there's too much computed runoff, which is consistent with not enough snow water equivalent. Later in the water year here for April and May, we're seeing more observed flow because of that larger snowpack that's now melting. That was creating and computing a simulation run. Once we've looked at the results, we're on to the next task. I'm calling task 4, calibrate the gridded temperature index. At this point, it's up to us to modify some of that input data, rerun the simulation, and then view the results. The first suggestion that it tells us to do is go back to the components menu, and then we'll go to the subbasin. Here's the subbasin element. I'm going to click on the snow tab here in the components editor. The first suggestion here is to change the temperature and base temperature to 34 from 32. So I'm going to go ahead and do that, click save, and then rerun the simulation. This means that we'll have more snow. That simulation has run. I'm going to click the results tab. Now I'm just going to select the observed snow water equivalent and the snow water equivalent right here. I'll click the plot. And now what we're seeing is a much better match between the computed and observed results, where the observed results are in red and the computed is in blue. The next step tells us to modify the melt rate function. I'm going to go ahead and skip ahead and look at the cold rate function and modify that next. The cold rate function what I want to do is increase the amount of snow we have up here without changing the temperature anymore. We'll keep that at 34. And then after that, we'll deal with the melt rate here because we have some air happening up here during March, April, and then later in the summer, May, June, July. There's another deviation from computed and observed. Okay, so back to the compute tab. Then I'll click on the subbasin again, and then the snow tab. I'm just double checking that we have cold rate here, melt rate there. I want to change this melt rate. We don't actually change the data here in the snow tab though. We would do that by clicking on the cold rate, which is right here. And then here's the table. So I'm going to leave the ATI values the same, but just change the cold rate function values from 0.01 to 0.05. This will be 0.10 and 0.20. Let's see what happens there. So I'll click save and then rerun the simulation. We'll go ahead and click on the results tab, expand that window a little bit. Observed snow water equivalent here and snow water equivalent right here. I'll click on the plot here. And with the colors updated, I can now see that this rising limb basically up until March or April, more or less, is a very close match. And now we have to deal with the melt rate later in the water year. So I'm going to go ahead and close this off, and then let's go back to our components tab. And then I'm going to select the melt rate now. So we got the temperature set, cold rate set, the melt rate right here. In the table, I'm going to change the values to 0.05. Okay, so basically the same values as the cold rate, and click save and then rerun the simulation. Let's take a look at the results. Then I'll click on the subbasin, expand that, observe snow water equivalent and snow water equivalent, and then click on the plot, update the colors. Now we have a pretty good match between computed and the observed snow water equivalent for the water year of 2017. Something else I wanted to show is in the basin model map here, I can just right click and then view results. And we have graph, summary table, time series table, but we also have this snowmelt graph when there's snow involved. And what we have is what we saw before in the bottom panel is the snow water equivalent, as well as the precipitation depth and the air temperature. So this is a quick way to get the same data in one single view. We're also instructed to view the results for the outflow versus the observed flow from this subbasin. We can do that in the results tab as well. Here's the outflow, and then here is the observed flow. So let me bring that up. And now we have a pretty good match, at least for the first part of the water year, with some significant deviation over in late April and then again June and July. If I zoom in here on like just 1 or 2 months at a time, we have the computed results in blue, and then that's a pretty good match right there. A very good match, very good match. And then we're starting to see some deviation here during the melt period. Step 4 says to continue modifying the remaining parameters, such as the wet melt rate, the cold rate. If I click on components here, what it's talking about is the subbasin here, the snow tab, Then we have all these parameters here. Here's the wet melt rate, the rain rate, the cold rate, and so on. And then to note their impact on the computed results, such as the snow water equivalent, the observed flow versus the computed flow at the outlet. So you're welcome to continue making those calibration changes and looking at the results. But that's it for this exercise. I wanted to conclude with something it mentions in the tutorial itself, specifically the answer to question 2 at the bottom. The changes to the px temperature and base temperature and the melt rate function resulted in the largest changes in the computed results. Well, that's it for this exercise. We talked about the gridded temperature index snowmelt method in HEC HMS.